I don't remember what we were talking about either.
Okay, everybody. So today the goal is we're going to learn once again about this new ICANN of IMFs. Then we are going to practice for our quiz next time. So our quiz for this unit is happening on Monday, which is the best way to do it, right? Because it's right before we go on break, and so we can just take it, and then you can go on Thanksgiving break and not have any homework or anything to think about, right? Which is the best way to do it. Okay? So with this idea of IMFs, it links directly back to what we learned last time with polarity. Can somebody remind us, for everybody and for those that weren't here, from what you understand for a smiley face, can anyone kind of describe to us what it means for something to be polar? Charged. Can you expand on that, Caleb?
Like magnets, like positive, good and negative, and negative, good and positive. Negative don't, good and negative, and positive, don't, good and positive.
Good. So a polar molecule results when the structure of it, so the structure determines polarity, right? There are two things we should look for to know if something is polar or not. Have a smiley face for your answer, by the way, Caleb. Can someone tell me one thing, when I look at a Lewis structure, what's one thing that will help me know if something's polar or not? Perfect. If it has a ghost, lone pairs, I should clarify this, in this class it's always going to be polar. I will say there are more structures we have not learned about as molecules get bigger and bigger, and actually when that happens, you actually do have some cases where something can have lone pairs, but it's not polar. But in this class, if something has lone pairs, 2 dots or more ghosts, it's always going to be polar. Good, have a smiley face for that. Can someone tell me what's the second thing you can look for to know if something's polar or not from a Lewis structure?
Random atom that is different from the others.
Good, asymmetry, right? Meaning there's 2 chlorines and 1 hydrogen instead of all just chlorine or all just hydrogen, right? If there's a mixed match of things, that's going to be polar, okay? So this idea of an intermolecular force, so that's what IMF stands for, is intermolecular force. The idea of an intermolecular force is this is what is describing this magnetism-like idea between the molecules, okay? Intermolecular means between, okay? 2 separate things, but there's a force between them, okay? I like to think of it as a friendship force because it's a molecule-to-molecule force. It's not an actual bond, right? The actual bond is the H to the O, right? This thing stuck to this thing, that's the actual bond. I can take it off, but it takes a lot more work. Okay, the intermolecular force is the force between. Okay, so on your paper, if you want to emphasize, it's labeled for you, but maybe circle it, right? This dashed line represents the intermolecular force. It's the force that this one feels in relation to this one. So just like we modeled in the beginning, if something is a solid, right, that means there's some intermolecular force that's holding it together. Versus if there's a gas, there's no intermolecular forces because they're not by each other. Gases don't have friends. They're too far apart. Okay? Questions on that? Okay. So we have 3 different classifications of intermolecular forces. Okay, the first one is known as a dipole-to-dipole force. This is the force that describes polar and polar things. Because if one thing is polar, it means it has positive and negatives. And so it can be attracted to something else that's polar with also positive and negatives. So whenever something is polar, then you know, oh, that substance has the dipole-to-dipole force. So our goal by the end of today is that if I give you a structure, just like before, so here's my Lewis structure. Okay, the goal is you should be able to tell me what IMFs that structure has. So, if I'm trying to see if it has dipole-to-dipole forces, the question is this molecule polar? Give me a yes or no with your head. Is this molecule polar? Good. Kate, how do I know?
It has the 2 dots in the bottom.
Perfect, right? That ghost up top is going to make it polar. And if anything is polar, it has to have the dipole-to-dipole force. Those are like, they mean the same thing in a sense. Okay? All The next type of force we have is known as a London dispersion force. Okay? I think it was Annabelle or someone back here. Last time when we did our Everybody Talks activity, somebody talked about, do non-polar things connect with each other? I don't remember, somebody back here. Is that you, Cameron or Annabelle? Someone back there, but. So with that idea, and I said, yes, they do. This is the force that describes that. So when something is non-polar, they still have the ability to track because of what is known as a temporary dipole. Okay? So a permanent dipole means the electrons are pulled in just one way, right? That's why we end up with the pink and the blue, positive and negative. But when something is non-polar, the electrons are always moving, right? Electrons don't stop, they're constantly moving. And in the game of probability, if you guys were electrons and I were to have you stand up and run around the room, and then I just said freeze, randomly, is there a chance that there could be more of you on this side of the room than that side? Yeah, game of probability, right? There's a chance there could be more here. Well, if you guys are electrons, and there's more electrons over here, that's going to make this side of the molecule negative, and that side of the molecule positive. Why, though, would we call this just a temporary dipole?
Because they're still moving.
They're still moving, right? There's nothing holding them to that side. In a polar molecule, it's literally tugging them across, and they stay there. So would you predict that this force is strong or weak?
Weak.
Really weak, right? But it's what justifies to us that even things that don't have an attraction can at times become a liquid or a solid. Because if things didn't have IMFs, they would never become a liquid. There'd be no reason for them to come together if there wasn't something holding them there. Okay? So the way I identified this one is if it's nonpolar or if it just has electrons. So these forces can be combined and things can have multiple forces. So my example here, let me move it off those words so we can read it a little bit better. Okay, so my example was NH3. Right, so we know in terms of our IMFs, why did this one have dipole-dipole forces? Because it was polar. So I know it has dipole-dipole. This is also going to have London. Because this one can, in a sense, do both. It can have the permanent dipole, but it also, the other electrons can cause a temporary dipole. So every single molecule on Earth has London. So the answer is always yes. Whenever you're like, what IMFs does it have? Always say London, because you'll never be wrong. Because every molecule has the London force. But particularly it's what explains why nonpolar things have an attraction. Okay? All right, so that's our second one. So we have dipole-dipole, London forces, and then the last one is known as the hydrogen bonding force. Now, keyword here, it's still just a force. Scientists called it the hydrogen bond, which I kind of hate a little bit because it can be deceiving in terms of like a bond. It's not a real chemical bond. It's still just the friendship between two molecules, okay? But with this hydrogen bonding force, this one is an extreme version of the dipole. So kind of notice the three things we've had. So we've had the normal dipole-dipole, is kind of the middle. You then have the temporary dipole, which is the London. Now this one is going the other way, and now we're going to an extreme dipole. So first off, the molecule still has to be polar in order for this to happen, because these things are additive. Okay? You can't have dipole-dipole without having London. You can't have hydrogen bonding without having dipole. Okay, so it's like the only way to have hydrogen bonding is this has to already be there. What causes it to be so extreme is the combination of two things. Number one, hydrogen, hence the name. Okay, hydrogen must be in the molecule, but then it must be bonded to nitrogen, oxygen, and fluorine, or fluorine, I should say. NOF, N-O-F. It has to be one of those three. Look on the periodic table. It's kind of nice. Find those three on the periodic table in front of you really quick. Yeah, they're all like right by each other, so that kind of can help just NOF, right, those three. So what we're looking for is one of these three bonded to your hydrogen. What causes it to be so extreme is, number one, these molecules have a very high electronegativity, so they're super strong in the tug of war. Okay? They're really, really strong in the tug of war is what makes part of it strong. The other part is the thing they're pulling away is the hydrogen. How many electrons does hydrogen have? It only has one. And so if you pull away the only one electron it has, what's behind an atom if you remove all its electrons? Just the positive nucleus. And so it makes it an even stronger positive force. Okay? You have this picture. Is everyone okay on these if I go to the next one? I want to draw on that picture that's also on your notes. Oh, wait, where's this thing? They're not going to show it here. Okay, I'll just draw it off the side. Okay, look at that picture of water with me really quick, and I want you to draw some of these. Okay? So you have this already. So your OH, and then it shows this. Everyone see that picture? Yeah? Okay? So this right here is the hydrogen bond. Once again, the two things that are happening are, number one, the oxygen is pulling the electrons away from hydrogen, and so it's becoming very, very negative. In this one, the same thing is happening, but this now becomes like super positive because the hydrogen has lost all its electrons. And so that's the hydrogen bond. Positive holds on to negative. And it's extreme because it's much stronger than just a normal polar bond. Questions on what it is? Okay, once again, all of these come back to it's about positive and negative things being attracted, whether it's a stronghold or just a temporary weak hold. Okay? All right, let's go through the scenarios and then we'll practice some problems here. Okay? So once again, this is kind of just summarizing what we covered. So the dipole to dipole is the charge attraction between permanent dipoles. Oh, let me come here really quick to our example. So NH3, to check if it has hydrogen bonding, I check to see does it have H? And is that H directly connected to NO or F? Yep, and so this one would also have hydrogen bonding. Okay? Okay, so all polar molecules have this force. It's the medium in our strength category. And it's going to get stronger as molecules get closer together. So the key thing, if I want to know if something has a dipole force, is I just have to figure out is it polar or not. Okay, everybody okay there? All right, summarizing the London force. So London is the temporary dipole that happens because of an unequal distribution of electrons. All molecules have this force. So once again, on the quiz, you're guaranteed a point because you just have to say, yes, it has London, even if you don't know anything else because everything has London. Okay? It's the weakest of them, though, because it's just this temporary. But it can get strong if molecules get bigger and bigger because they have a lot of electrons. And so if you have a lot of electrons that can randomly move, it can have a much stronger force than others. So certain big molecules have a pretty strong London force. Okay, and then last one on our table, summarizing our hydrogen bonding. Okay, so this is the extreme attraction between NH, OH, or FH. Once again, it's called a pseudo bond because it is strong, but it's not a technical chemical bond. Right, there's no electrons being transferred, it's just molecule to molecule force. But I would guess most of you have experienced the strength of this force in your life if you have ever belly flopped into a swimming pool, whether on purpose or not. Because when you hit the surface of the water, the reason why it hurts is because the water molecules are playing Red Rover against you. And if you hit it flat, you lose. right? That's what you're feeling, is you're feeling the hydrogen bond force, is those molecules held together, and so when you hit them, right, they don't pull apart. I mean, it's literally why, like in Lake Powell, it's like illegal to jump from certain heights, because you could actually die from hydrogen bonding, right? That force of the water can be so strong from certain heights. Yeah, Sam.
Isn't hydrogen bonding also used, doesn't that help water being protein reaction, kind of capillary action?
Yes, yeah, great point, Sam. Have a smiley face bring that up. So with water, like if water didn't have hydrogen bonding, like things wouldn't function like they're supposed to. Like it plays such a critical role in like our human bodies and what it does, as well as for plants, because of its hydrogen bonding. So yeah, and that's what we're gonna get into next, is kind of the application side of it. So, okay. Questions on this for now? We're gonna try some practice problems here. Okay, we're gonna skip this section here real quick because I want to do practice before we get into the application. Turn the page over to this chart right here that says which IMFs are present. Turn to this here, everybody. I'm gonna do the first two with you, and then I'm gonna have you try the last four for some smiley faces. Okay? All right, so let's go to the chart first, and then we'll come back to this. Okay, so looking at the molecule, first question: does it have London dispersion forces?
Yes.
Yes, because it always does. So put a check mark. Yes, it does. How do I know if it has dipole to dipole forces? If it's polar. So is this molecule going to be polar? Yep, right here, right? Lone pair. So this is the polarity question. So if it's polar, then yes, it's going to have dipole forces. If it's not polar, then it wouldn't. Okay? What do I check for with hydrogen bonding?
H is connected to
Good. H connected to O, N, or X. Which in this case, there's not even H's, so it can't have hydrogen bonding. So I'm going to put a big X as no. Okay? Let's do one more together. So looking at this molecule, so does it have London forces? Always. Dipole forces, this one is not polar because it doesn't have lone pairs and they're all H's, right? It's symmetrical. Hypothetically, I guess I won't give it away because the next one has that. But if one of them was different, then it would be polar. So in this case, it's not polar, which by default means it can't have this. Because to have an extreme dipole, you at least have to have the medium dipole as well. You could check it and see still, but it's impossible to have the last one without the middle one. Okay, questions before I send you off with your table buddy? Okay, try the next four with your table buddy, and then we'll check them for 4 smiley faces. So check marks or X's, does it have that force or not? Ready, go. 4 minutes? 2 minutes?
Wait, you said it can't have H.
Wait,
well,
no,
I mean,
this wouldn't
can
be
this be
ever because
polar
there's
because the
no H.
Yeah, it would be
connected
polar,
to-
yes.
Okay.
Oh, yeah.
So then it doesn't have
Oh,
hydrogen
that,
bond.
it doesn't.
Why not?
Well, because the H's aren't
Not
bad.
bad.
It's not connected. It has the 2 pieces, but they have 2 pieces.
Wait.
This one because it's connected to O. This one is just going to be.
It's not bad.
You're late, Casey. I know. Wake up, bro.
Casey, you know how we beat whatever Louisiana by like 4, 7 last night? Auburn only beat them by 15.
Really?
Yeah. And
Auburn sucks.
That's
They
weird.
look
I didn't know that, but I did dream BYU. I did dream that BYU played Auburn in basketball.
Actually?
Auburn's bad, so they're not winning anything. Casey, you're on the wrong side. We'll call them. Is it hard or? No, it's pretty easy.
Yeah, you just have to like You just have to remember.
And then will you show me some of the homework?
We haven't done it yet.
Okay, wait, so what do I do?
Okay. Just
So,
guess cases.
all of them always have LD. No matter what, it's always.
They always have LD?
Yeah.
Even if they're gay.
Yep, even if they're gay. Bro goes. Okay. DD is if they're polar.
What does that mean?
The things we did last time. So if it's polar, it has the ghost.
Like that ghost? What's a ghost?
These are the ghost.
Okay.
And then this one is if it has H's and it's connected to NO or F.
That has hydrogen and it's connected to
To N, O, or F.
So those are like patterns.
Is that right?
Yeah.
So does this one have ghost? Yeah.
Which one?
This one has a ghost?
Yeah.
How does this one have a ghost?
Oh, I'm retarded. So no, never mind. Then this has to be wrong as well.
What?
They both have to be wrong.
Wait, these ones?
Wait,
Yeah.
why
Because
is
there's no
that?
ghost.
Why is
That one it only works. HB only works if DD is working. Because there's no ghost. It has to be polar first.
Oh, it has to be polar
It
first.
has to be polar. So DD obviously has to be polar, and then for HB to work, it has to be polar, and then I
Okay,
think
let's go through this and make
That's
sure
the
we're on the
most
right
random
track. So
crap.
looking at this one first, let me know if you got any of them wrong and you don't understand why. Like, this is the time to ask so we don't make mistakes on the next time. Okay, so this one, yes, it has this. Yes, it has this. No to this. So if you have yes, yes, no, have a smiley face. Any questions on that one?
wait, how is it polar?
So two things for polar, right, are dots
Oh
on
wait,
the
I'm
middle.
the third one. I was looking at the
Oh,
second
you're looking at the
Yeah,
wrong
yeah.
one. Okay. Any other questions? The third one. Yes, yes, no. So yes, London, yes, dipole, but no to hydrogen bond. Okay? Now, something some students might say, if they were to get this wrong, is they would say, but it has an F, it has an H, why doesn't it have hydrogen bond?
She hasn't checked
They're not connected, right? They have to be connected. There has to be a bond between them to be the hydrogen bond. Okay, very good.
Wait, no,
Okay,
you're
next
right, Kate. Never
three
mind.
coming here.
You're not a
So
loser.
your CO2 molecule is yes, London forces, no, no. It's not polar and doesn't have hydrogen bond. Questions on CO2? Okay,
Why is it?
this one
Because of them.
is
Because
yes,
he's
yes,
good at these things.
yes. Yes,
that was
London.
No,
yes,
I
it
did
is
have it
polar.
polar.
Yeah, I told you.
So this one is showing you a 3D
Oh, 'cause it's
shape.
lifted up.
Oh,
because
and
it's
the
lifted
height
up.
that
Yeah,
goes.
it goes.
Yeah, so the only way to
Kate,
be
I
bent
really
is
believed
there
in
had
you
to
for a
be
second.
So is
but-
he the loser?
Yeah, so I was right all along, I guess.
Any other questions on this
Yeah,
one?
I had realized it was Ben at first, and then I forgot.
Last one here.
Feels good to be right about everything.
Yes, London.
He says it's here.
No, no. So it's not polar and it doesn't have hydrogen.
Because it's still
Hey,
connected.
you're an idiot.
I just
Questions
didn't know that
on
one
this
thing.
idea of identifying
So is it
IMFs?
just like if it's a mirror image? then
Yeah, it's a mirror.
Yeah, so smiley face, so up to 4 smileys for each row you got.
This is funny.
Any questions?
Oh,
Up to 4. Yep.
I'm dissolving.
Shut up.
That's easy for you to say. You're not polar.
No questions on the identifying side?
Also have photography.
Well,
Oh yeah.
Yes, we're gonna finish up those last columns of just the identifying thing.
what about Brad?
Yeah.
Can't tell you.
Okay.
You I had to be there.
What?
I had to be there.
Where?
Okay,
You
so
had
the
to be
last
there.
thing we're gonna
When?
look at here,
Why?
everybody, is
Guys,
once again the
it's not a
application
good
side
thing.
of
Is
the
he gonna be
IMF.
there?
And differences we see in their properties because of their different intermolecular forces they have. So some of the different things that track back to intermolecular forces are melting and boiling points,
Oh, that's fine.
okay? Cohesion, which is the ability to stick to like each other. Surface tension, as I mentioned before, right? That's like on the surface of water, okay? And then the last one that we're going to look at is this idea of like dissolves like. Okay, so we're going to show you a few demonstrations as we kind of talk about these properties. I'll let you get them kind of filled in so then you can just focus on listening. So once again, you should have flipped back. There's a few blanks on the page before and then a few right above the table. Okay, so let's start with boiling and melting, okay? So if I have a molecule and it is in a liquid state and I wanted to change it to a gas, right? In a sense, that is a process of evaporation or boiling, right? It's adding enough energy so that those molecules can break apart from each other to become a gas. So let's make a little connection here between IMFs and boiling point and melting point. So if something, make this just off to the side somewhere on these to kind of bring it together. So if something has a high or a lot of intermolecular forces, okay, meaning it has London, it has dipole, it has hydrogen bonding. If something has a lot of forces holding it together, don't say anything out loud, but just think in your head for a second. What would that mean about its boiling point? Would you predict that something with a lot of forces, once again, don't say it out loud, but just think for a second, is that going to have a high boiling point or a low boiling point? What's the relationship there? Don't say anything out loud, but think for a second. Great point, Caleb. So IMFs only exist with covalent molecules, which is why like it's followed like after Lewis. But yes, great point. Because that it kind of goes in somewhat the same, but it's a little bit different. Okay, point with your finger. Do you think high, low, or if you're unsure, point in the middle? Okay, so does having high IMFs mean you're going to have a high boiling point? It's going to take a lot of heat to break them apart? Or a low boiling point would mean you don't need much heat to break them apart? Good. If you're pointing to the ceiling, have a smiley face. Good analysis there. Okay, now let's show you an example of the opposite. Okay, so obviously water takes a lot of heat to boil. Nitrogen is, by itself, is just N to N. It's the last one on our example. Okay, so I'm going to pour out some liquid nitrogen for us, and we're going to see it boil at room temperature. It actually boils even like much colder than room temperature. But to show you that this one has like, it only has London forces. So there's really not much holding these molecules together. And so when they have a chance, they just spread apart. Okay? All right, let me pour it down here and then I'll bring it up top. I just can't lift this high.
Jason, you better be ready for the photo.
Why?
Be prepared.
There's gonna be crazy things happening.
So Bryce is going to tell you something.
Actually,
better
no.
be prepared.
I'm siding with Bryce on this.
All right, it's going to go pretty quick.
Don't
So
ask.
this is liquid
I'll
nitrogen
football today,
boiling.
I'm only gonna pass it to Bryce.
Now, unlike water, which would
I'll be
burn you, if you
quarterback
put your
then.
hand in this, it would.
Then I'm
Right, so this boils at like negative
But Bryce doesn't either, so Kate's better.
270 something.
What are they? Kid will pop up.
Kate will pop up.
We should just run a bunch of drag routes all the time. And then someone should just, we should just screen each other.
Very similar to dry ice.
Triple
Dry ice
screen
is like
someone.
no IMFs. So it just turns to reactor.
I'm so down for just run that and then just like block. Just like off the block.
Just run a wide receiver screen every time.
So one of the, that's why I have it in water
that?
actually, but if you like let it in there long enough.
Jeremy, you drink that?
Die, yeah.
Well, he was asking.
Austin
Yeah,
goes,
it'd be
oh,
very
Lord.
bad for you.
What if you just had like one drop?
Just a little bit.
It would like burn off your taste buds.
That would hurt.
It would be like very dangerous.
Wait, if it like, so it would burn my hand too?
Burn in terms of freeze.
That's the
So
stuff
it
they
would still-
use. That's the stuff they use at Sub-Zero.
So as it like cools down, so I'm gonna speed it back up. So it's still boiling. If I look in there, I can
Wait,
still
it's
see
like
bubbles.
this stuff? Remember
But I'm
this
gonna add some
Yeah.
warmer water because if I raise it even higher, then it's gonna boil away even quicker. Right, and so like, once again, there's no IMFs in nitrogen. That's why normally it's always just a gas. To make it a liquid, you have to cool it down so much because those molecules have nothing that wants to pull them together, right? This, by the way, is the same stuff like if you go to Sub-Zero, right? They make liquid nitrogen ice cream. We'll play with it more throughout the year in various different ways. But okay, let's go to our next one with surface tension, and I'll show you a little demo.
Even my pencil's great.
So if something has high IMFs, don't say it out loud, but I'm going to have you make a prediction here in a second. Make me a prediction about its surface tension. Okay, don't say it out loud, but same thing. If something has high IMFs, what does that mean about its surface tension?
Lower surface tension. So it can.
Okay, everybody ready? All right, we're going to try to do this uniformly because if you delay, then I just assume you're looking at everybody else. But I want to see your honest answer. Okay, so when I say 3, show me your sign of up, down, or you can give me an unshort. That's fine too. Okay, ready? 1, 2, 3. Point.
Grant was looking at me, got him.
So the connection is high.
Yes.
Yep. Because remember,
He was
IMFs
staring
are
down.
linked together.
He just thinks I'm
And so if
smart,
something is
little
linked
bit
together
smart.
strongly, then its surface tension is going to be strong. Okay? I think we
Crane's
might have
over
froze our
too.
water too.
I'm also, well, I did unsure, so.
There's definitely a layer of ice in there. Okay, so to show us surface tension, I'm going to use water. Okay, so what type of IMFs does water have?
Green water.
All of them, right? It has London, it has dipole, it has hydrogen bonding. So we know water has a pretty high surface tension, which, like I said, you've maybe experienced before with belly flopping. Okay? I'm going to show you surface tension in a reverse way, but once again, shows you it straight still. So I have a little jar I filled up with water. I'm going to get a card here. Too many things going on back here.
Jeremy, I'll just belly flop in that.
You'll just volunteer.
Into the cup, yeah.
Figure it out.
What could go wrong?
All right, I'm just using a little laminated piece of paper. Okay, that fits over the lid of my jar. Okay. All right, so I have my jar, have my paper. Everybody ready?
She's gonna flip it upside down.
I'm going to flip it upside down. Are you ready?
What?
Right? So surface tension,
Crazy.
the water molecules are holding on to each other.
What?
Wait,
Do it again. I have that to my sibling.
Bro, she
not real.
she has to be playing for that.
I might be playing. It is real, but there might be a slight magic to it. I'll show you the magic.
She plays for the Astros. She cheats. Casey.
Okay, water. Oh, I filled it up a lot this time. Ready? It is a special
The way she's.
Okay, so it's not, yes, it is not quite real. But it is real in that the water isn't falling through, but I've given it something else to hold on to besides just the tire gap. So I glued a window screen to it. Okay. But it's still quite amazing that the water molecule can hold on to the window screen, hold on to each other, and not fall through. Isn't that pretty cool? Obviously, I'd be curious to know, like, what's the max you could do? Like, what's the biggest hole size that they could go across? But even this, like, that's a tiny hole, right, Cade? But how many water molecules are probably across that distance?
A lot.
Billions. Imagine a billion people holding on to each other across the Grand Canyon and not falling.
Break your arm.
That's pretty amazing, right? Like the strength of the hydrogen bond, even though to us it seems like a pretty small thing, right? Okay, so that's the one to kind of think about surface tension.
Casey, shut up.
Can you dunk from the 3-point line?
Okay, so like dissolves like.
On the opposite
Okay.
hill.
Now with this one, so the other two were like a comparison of if this is high, that will be high. If this is low, that would be low. With dissolving something or mixing, it's not so much about high and low as it is about similarities. Okay, so I just have some plain vegetable oil here.
Are we lighting it on fire?
No, not lighting on fire.
Light it on fire.
Case and me and Colin were saying that for halftime.
Okay, I'm gonna
spaces,
add
have like a
some
student dunk
water.
That'd be sick.
And as we're all pretty familiar with, do water and oil mix with each other?
No.
No, they don't, right? Like, so if I pour this in, a little bit more water, right? We see the separation. If I stir it around, it will mix momentarily,
Go out when it's raining.
right?
They don't mix.
But it will then separate back out.
It doesn't work. I'm gonna have to try it. Casey, do you want to try something? Sure. Okay.
Okay,
It's raining today, so.
sorry, my thing was a little dirty, so it's kind of separating out, but we'll get there. I should have put the water in first. Okay, so water and oil do not mix. Okay, now a lot of people would talk about the density of it, that it's because they have different densities. The density only describes why one is on top and one is on the bottom. What really is causing them to mix is whether or not their forces interact. When their forces can interact with each other, then substances will mix. Otherwise, the water, because water has what type of forces again? All of them. So water holds really tight to itself. Oil only has London dispersion forces. And so there's no reason why the weak forces of this can penetrate into the strong forces of the water. So it's not really about a repelling, because sometimes people say water and oil repel each other. They're not repelling. It's just the water is holding on to the water, and the oil is holding on to the oil, and they're not going to pull each other into one another. James. Love that question. Have a smiley face. Theoretically less. It should. Yes. So if anyone wants to volunteer and belly flop into oil, I don't have a pool to do that in.
I have the pool. Give me the oil.
But yeah, but theoretically, the surface tension is less with oil than in water.
That go crazy.
It starts raining.
All right, now here's your challenge question, everybody. Okay, give me your eyes up here. Give me your eyes up here, everybody. Okay, I'm gonna add food coloring to our container. Okay, that's what I want you to answer. Is based off what you observed, what can you tell me about the IMFs of my food coloring? Okay, so observe, and then that's in a sense what you want to try to come up with, is what are the IMFs of my food coloring? Okay, all right, everybody ready? It's a little bubbly, so
How would it get through the oil to get the water then?
okay, so here we go. Add a few drops in so you can hopefully see them. Everybody see it?
No, you didn't tell me it's to sink.
I said it would go through the oil.
Hold on. Okay. Help me get through all those bubbles. So first off, you can hopefully even make a claim because of what it's doing in the oil. Oh, we're almost there. Oh, we're almost there.
Yes. Just let me drink all the water out.
What?
Is that gonna be long enough? Ooh, I don't want to do that.
Just drop it. Just drop it.
Kate's pencil. I can just use my
Yeah,
finger.
yeah. We can use this pencil.
You want me to dip your pencil in oil?
It's not my pencil. It's Creighton's.
Okay, doesn't seem to mind.
You can't. If I dip your pencil in oil.
All right. Okay, here you go. So I'm just going in. It normally like will go on its own, but we just don't have time to keep staring at it. So I'm just gonna give it a little boost to get down to the water. Oh no. There it goes.
Wow.
So notice how it interacted with the water, how it interacted with the oil, and what can you tell me about the IMFs of my food coloring? Okay, turn to your table, buddy, and tell them your thoughts. Ready, go.
Looks like a sperm cell. Oh yeah.
Did you know that
Sperms don't actually swim like this. They have coils and they. Obviously, they wig.
Shut up! What?
I mean, they're all learning scientific fact.
This is technically science.
It's life
I mean,
chemistry.
yeah, okay.
I don't know if the life reproduction has to do with chemistry, but
It does, because it's all chemistry. We're
It's
made of
mixing
chemistry.
and mingling.
Austin,
Kason is chemistry. I'm gonna call you chemistry.
I'm going to call you the chemist. That goes
The
hard.
chemist. Kason the chemist.
Casing the,
I'm gonna call you
Casing the registered sex offender.
I'm gonna call him
Okay, let's hear some thoughts. So we're gonna have one person from each table is gonna have to speak. Okay? Once again, you can share somebody else's idea, but you're gonna be the spokesperson. So the way we're determining it is everybody look at your atom card. Look at your atom card on your corner. Whoever has the least number of no, we did that last time.
Yeah, we did that.
Whoever has the most protons, stand up.
I was like, I heard
we even
I
say?
was like, no.
You are set. What did we even say?
Oh, yeah, because they're in the middle.
It was green, and it looked like a
Get
sperm
in there.
cell.
Okay, stand up if you're the chosen one. Be proud of being the chosen one.
Ours are like together. I want to go second.
Okay, close your mouth.
Actually, no. Have I ever told you
Now,
that you look like
as always, whenever we play this game,
Pavilion?
only one person should be
I
talking,
bet you love the Grinch.
which is me right now. Okay, so if you're not the called on one, you should be listening because what they have to say is going to deepen your own understanding. Now, if your person's standing and someone else says a similar thing to you, you can say it again, right? Repetition is how we learn. Once again, or you can always ask an extending question. So if you like have a question about it that you're like, I get this, but I have this question, you can always ask a question instead. Okay? All right, Ice is going first.
Crane said water was stronger than oil.
It's true, so that's not a bad claim, right? That the water does have stronger forces
Say the same
than
thing,
the oil.
Kate.
That's getting us where we need to go. Thanks, guys. Have a smiley face for that. Okay, who wants to go next? All right, go ahead, Kalia. Perfect claim. We saw the food color interact with the water, and so if water's polar, love that. Have a smiley face. Caitlin.
We said that we know.
Oh wait, time out. Zip your lips. Caitlin's talking. Go ahead.
We said that because the water is polar, we know that it's at least dipole-dipole, but we weren't sure if it was
Ooh,
hydrogen bonding.
love that, right? Like we can make some claims, but maybe we can't know it all. Like, did it go all the way to hydrogen bonding? So in clarifying that a little bit, yes, if something has dipole and dipole, they'll mix, even if one still has hydrogen bonding. Hydrogen bonding would just make it even more soluble, but it doesn't like prevent things from mixing. Good claim. How's my face that? Who wants to go next? Who's ready with something? Kelly.
We said stronger surface tension than oil, but weaker surface tension than water.
Ooh, so stronger surface tension because it's holding together in the oil, but then it was weaker in the water because it spread out. Love that. How's my face? Sam.
So that's kind of like Bison. It has stronger IMFs in the oil, but it's weaker in the water because it breaks apart in the water and then it bounces.
Good, and then mixes around with it. Good, thank you. How's my face for that?
Why did the food coloring drop all the way to the bottom of the water too?
So that was super interesting, and it's never happened before when I've done this demo. You haven't seen it, and I'll tell you. So Kate asked, why did it drop? So like, it went through the oil, right? And then when I poked it, We saw it stay as a ball and go all the way to the bottom and then it burst open. Normally it actually bursts as soon as it hits the water. Here's my prediction. I don't really know why. I've never done that before. My prediction is that, if you hadn't noticed, so I used this same flask for this demo because oil's so hard to clean, right? And normally I try to clean a little bit better, but it wasn't super clean. And so there's actually oil kind of coated throughout all of it before I even started. So my prediction is that some of the oil was still kind of stuck to the droplet as it went through the water, so it stayed together. But then it kind of dissipated and then it broke open. But yeah, great observation, Kate. I have a smiley face for that. It's actually somewhat similar. Why? And we'll do it at the very end of this term. You guys know bursting bobas, right? Like bobas that burst open, right? Like those, in a similar way, are all about IMFs, right? And so at the end of the term, we'll have a lab where we'll make some, just to see like the science behind it. So, Becca, do you want to go next? Okay, Becca's talking. No one else should be. Perfect. Like dissolves like, right? Similar things attract to similar things. And Moody, what do you got for us? Good, right? The IMFs are stronger than the oil. Once again, when we're looking at like dissolves like, it is a little bit about strength, but it's more about similarity. Okay? That's why in cooking, if you ever want to dye something, so they do this like with candies and things, if you ever want to color oil, you have to buy a different type of food coloring. Because normal food coloring is water soluble, meaning it dissolves in water, but you can actually buy fat soluble food colorings to dye something that has a lot of oil in it, particularly like chocolates. Like if you're trying to color chocolates, like if you have white chocolate and you add normal food dye, it won't work. Because the chocolate has a lot of fat in it, and they're non-polar, and so they don't mix. So you have to buy a special kind of food dye to make that work. So, okay, questions on any of these properties before we practice it all? Okay, all right, here's what's going to happen for our